Hello. So for this video, we will be talking about another example of Newton's law of cooling application of first order DE. So the problem goes, a body at an unknown temperature is placed in a room which is held at a constant temperature of 30 degrees Fahrenheit. If after 10 minutes the temperature of the body is 0 degrees Fahrenheit and after 20 minutes the temperature of the body is 15 degrees Fahrenheit, find the unknown initial temperature. Okay, so it says here that the call this one, the ambient temperature is 30 degrees Fahrenheit. At the same time, we are looking for the uh, unknown initial temperature. Okay, so we are looking for Q when time is 0. Also, other given here, if after 10 minutes the temperature of the body is 0 degrees Fahrenheit, so the temperature is 0 degrees Fahrenheit when time is 10 minutes. Also, after 20 minutes, the temperature of the body is 15 degrees Fahrenheit. So Q is equals to 15, okay, when time is 20. Okay, also, I would like to point out that if we look at the trend here, okay, so as the temperature increases, the temperature of the object is also increasing, okay? In other words, okay, the initial temperature of the object is less than the ambient temperature. So if this is the case, we can use the formula we have mentioned in the previous video, okay, that we can interchange Q and Q sub O depending on who is larger. In this case, Q sub O is larger. So Q sub O minus Q. Okay, so this will be our working equation. Then here, our Q sub O is 30. Okay, so we can perform variable separable solution for this one. dq over 30 minus q is equals to k dt. Right? We can integrate both sides. So this is negative. Okay, so the derivative of q is negative dq. That's negative here. So negative ln of 30 minus q, okay, is equals to kt plus c. Okay, so if we want to eliminate ln, we need to get rid of the negative first. So we multiply negative on both sides. Okay, and we will have ln of 30 minus q is equals to negative kt plus c. Okay, so to cancel ln, we make it the exponent of e. Okay, so e and ln will be cancelled. 30 minus q is equals to c1 e raised to negative kt. Right, now for the given, it said here that first given at time 10, okay, q is equals to 0, right, 0 degree Fahrenheit. So we can substitute this to our equations. We will have 30 minus 0 is equals to c1 e raised to negative k times 10. Okay, so 30 is equals to c1 e raised to negative 10 k. Now this will be our first equation. Since we have no k, okay, we cannot simplify for c1. Now we will use the second example, or rather the second situation, okay, using the same equation here. So we have 30 minus q is equals to c1 e raised to negative k t, and this time t is equals to 20, q is equals to 15 degrees Fahrenheit. Let's confirm if it is correct. Yep, 15 degrees Fahrenheit when time is equals to 20. Now let's simplify this one. So we have 30 minus 15 is equals to c1 e raised to negative k 20. Okay, so 15 is equals to c1 e raised to negative 20k. Right, so these are our two equations with two unknowns, C1 and K. Okay, let's call this equation number 2. So to solve for C1 and K, we need to combine these two equations. Okay, let's combine these two equations. Starting with equation number 1, let's simplify equation number 1 and to C1. Right? C1, let's transpose e raised to 10k to the other side. So 30 e raised to, okay, so e raised to 10k transpose to the other side, so the exponent will be positive. So e raised to 10k. Let's substitute C1 to our second equation, right? So this will be 15 is equals to, so C1 now will be equal to 30 e raised to 10k, right? Times e raised to negative 20k. And then we will have here e raised to 10k times e raised to negative 20k. So we can they have the same base, so we can combine the exponents. Okay, so 15 is equals to 30. This will be e raised to 10k minus 20k, right? And then 15 and 30 can be combined. So we will have 15 over 30 or 0.5 is equals to e raised to negative 10k. Then we can extract k from this by applying ln on both sides of the equation. So this will be ln of 0.5, then ln and e will cancel out, so negative 10k. So k now will be equal to negative ln of 0.5 over 10, okay, or 1 over 10 negative ln of 0.5. Now this value of k, we can use this to solve for c. You can use this equation, okay, right? So for c1, we will have 30 e raised to 10k, right? So c1 is equals to 30 e raised to 10k, then 10k will be negative 1 over 10, right? ln of 0.5. Okay, so in this case, negative 10 and 10 will cancel out, so we will be left with c1 is equals to 30 e raised to negative ln of 0.5. Okay, then so we can cancel e and ln. We need to simplify the negative sign, so 30 e raised to ln of 0.5 raised to negative 1. So e and ln will cancel out, right? So c1 is equals to 30, so 0.5 raised to negative 1. So 0.5 is 1 half raised to negative 1. Then we can simplify 1 half raised to negative 1. It will become 2. Okay, so c1 now is equals to 60. Right, so let's take note of this. c1 is 60, k is negative ln 0.5 over 10. Then we can use these values to our equation. So let's use this one. Okay, so our equation now will look like this. So 30 minus q is equals to, okay, c1 is 60. 60 e raised to negative k is negative 1 over 10 ln of 0.5 times t, right? So let's rearrange. So q will go to the other side, 60 will go to the other side. So q is equals now to 30 minus 60 e raised to. Now this one, negative, negative, so positive, 1 over 10. Okay. ln of 0.5 times t. Again, we will not try to simplify this first. Okay, so for the question of the problem, which is the initial value. So we're looking for q if time is 0. Okay, so what will happen here is q is equals to 30 minus 60 e raised to 1 over 10 ln of 0.5 times 0. Okay, and then this part here, so e raised to 0 will be equal to 1. So therefore, q is equals to negative 30 degrees Fahrenheit. So this will be our initial temperature. Okay, so that's it for this problem. Again, part 2 of Newton's law of cooling. See you on the next video.